Take a look at the new reference sheet that you received. You'll notice first that there's a long list here and a shorter list here. You do not have to memorize these lists. It's a reference sheet that you'll be given on the test. All right, we'll learn how to use these lists. They're called the activity series. We'll learn how to use them today. Down here at the bottom, you'll see descriptions of single and double replacement. And those are the two types of reactions that we're going to be covering today to finish out our types of reactions. That'll be all four will be covered. So keep this handy. I'm going to be teaching off this bottom part here. This won't be given to you on the test, but it does have your basic descriptions. If you look at single replacement, the third type of reaction, you'll see a skeleton reaction there like what we had yesterday for synthesis and decomposition. It's best described as a free element reacting with the compound, which is different than anything we saw yesterday. A compound and a free element reacting together. For example, single replacement. Right, the example. This is just the skeleton. Yeah. I know this is single replacement because it's a free element reacting with the compound, yeah? If you look at that reference sheet, it will tell you what you're supposed to do. It says that to predict the products, the entities over here that share a charge want to switch places. Now, here's what I mean by that. If we were to label everything over here just by its general charge, you would say that it's plus, plus, minus, right? You can look those up. I mean, there's numbers there, but +1, +1, -2. In a single replacement reaction, the items that share a charge want to switch places on the product side. However, sometimes there's a no reaction that'll take place. For example, what is this made of? Silver. If she loves me, it's silver. I don't know for sure, but silver, all right? Ag, that's a free element. If I were to drop it in water, H2O, a compound, free element into a compound, single replacement, what would happen if I dropped this into water? Nothing. The point being, just because you mix stuff together doesn't mean something's going to happen. And you have a way to tell if a reaction will take place. Look at that reference sheet again. That's got the long lists on it. Again, these are called the activity series. And here's how you use them. For the reaction to happen, whichever element is the free element, in this case sodium, it needs to be higher on the list than the element that it's trying to swap with. Listen again. The free element needs to be higher on the list, and that's one big list, guys. It needs to be higher on the list than the element it's trying to switch with. In other words, is sodium higher than hydrogen? Those are the two pluses on the activity series. Yeah. Find it. Is sodium higher than hydrogen? Yes. So the reaction will happen. So let's watch it happen. So all that's happening, guys, is the hydrogen and sodium are going to switch places. All right. So that means the plus sign is going to stay where it is, and the oxygen's not moving, right? So I put the plus sign and the oxygen exactly where they are because they're not going anywhere. The only things that are swapping are these two guys that have the same charge, meaning that hydrogen will now be by itself, and sodium has come over here with the oxygen. Check what you wrote. Free element. Is he diatomic? Yes, hydrogen is diatomic. Compound. Check charges. +1, -2. All right, none of this stuff is your answer. This is just all my work. But sodium reacts with water to form hydrogen and sodium oxide. do another one. Write this down. I know it's single replacement because there's a compound and a free element reacting together. It doesn't matter which comes first. It's an addition problem, right? 2 plus 3 is the same as 3 plus 2. So it's single replacement. If I identify charges, I know transition metals are always positive, nitrate's negative, gold's another positive transition metal. And the ones that share a charge want to switch, but make sure they will. On the activity series, the free element must be above the element he's trying to swap with. In other words, is gold is gold above copper? Gold is not above copper, therefore we don't even have to do any more work. No reaction. Nothing will happen. Now, we could theoretically still predict products. You could still swap them and do everything. But usually you don't have to. The only reason I point that out is there's a couple questions on my assignments that will say, find the theoretical products anyway, just because my point is to make you practice. But never find them if I'm not specifically saying find them anyway. It's a no reaction. You try one. Predict those products. I know that it's single replacement because it's a free element reacting with the compound. If I look at the relative charges, they look like that, so it's the two anions that are going to try to swap. But for it to happen, the free element must be above the element it's trying to switch with, so chlorine must be above bromine. Is it? It is. So the reaction will happen. The plus is not going to move, and the potassium's not going to move. That's a real good way to kind of keep your bearings while you're doing this. Is first write down everything over there that's going to stay put. And then swap the two guys that are switching. Now bromine's by himself. And now chlorine has come over here with potassium. Check nomenclature. Free element. Diatomic. Compound. We're good. +1, -1. And that's it for single replacement. There's no other twist. Just know how to use the activity series. And don't try to use the activity series on any other type of reaction, because you'll do that. Look back at the very bottom of your reference where it talks about double replacement, the very last type of reaction. Double replacement is defined as two compounds reacting together. But be careful. Look back at your F5. Your F5 had two compounds reacting together. Look, compound, compound, but I said it was synthesis. So watch for the subtleties. Look back at the reference page. It says two compounds reacting together, but neither of them water. So watch that, because if one of them's water, it's synthesis, not double replacement. Let's take a look at a double replacement. I know it's double replacement because it's two compounds reacting together. The nice thing is that this works the exact same as single replacement does, except we're not going to look at the activity series. If I look at the relationship of charges, it's plus, minus, plus, minus. All right, you can look all that stuff up. Those are the overall charges of each entity. And again, the like charges want to swap, but we're just going to swap the cations. We're just going to swap the positive guys. So the sodium and hydrogen are going to switch places. So again, a good way to do it is to first write down the stuff that's not moving. Hydroxide is not moving, and sulfate is not moving. Yes?
Will it matter?
What do you mean?
Like, if you just, instead of doing the cation,
It won't matter.
Okay.
Just don't switch them both, or you'll end up with the same things on the other side. Does that make sense? So, the H and the Na are switching. All right, so hydrogen's coming over here. Notice how I didn't bring hydrogens 2 with him. Look here, this is the most important point I'll make on double replacement. The thing that causes y'all's trouble sometimes are the subscripts. Whether or not the subscripts transfer over to the product side when you're moving things around. The only time the subscripts automatically get to move is if it's a subscript that's connected to a polyatomic ion on your paper over here. H2 is not on that paper. There's no H2 that you had to memorize for your polyatomics. The only reason he's H2 right here is because of what he's bonded to. But we've broken that bond. So he's not necessarily H2 anymore. However, look at sulfate. He did get to keep his 4. Why? Because of the exact same rule. I can sum it up in one sentence. The only subscripts that automatically move from the reactant side to the product side are subscripts that are connected to polyatomic ions. Like sulfate is a polyatomic ion that needs that 4 at all times. The H moved over to there. The Na is moving over to here. Check nomenclature. HOH is fine. There's a cleaner way to write him, though. What is HOH?
H2O.
Yeah, it's water, but I don't care if you leave it as HOH, whatever. But here, we've got +1 minus 2, so make sure that you are respecting the rules. Let's do another one together. I know it's double replacement because it's 2 compounds reacting together. If I look at the relative charges, it's plus, minus. It always will be for this. We're not going to react covalent compounds right here, right now. So you can make this assumption for now. So we want the 2 positive guys to switch, the cations to switch places. So I'm going to first write everything else over here. Nitrate is not moving, the plus sign is not moving, and chlorine is not moving. Notice the subscripts that I kept versus the subscripts that I didn't, based off whether or not those subscripts were connected to polyatomics. Ag and Ca are switching places. So calcium's coming over here. Silver's going over here. Check what you wrote. Calcium's +2, nitrate's -1, so we've got some stuff happening here. What's silver's charge? Who knows?
1.
It's always 1. It's one of those like cadmium and zinc that's constant. And chlorine's also 1, so he's good. All right, and it's not balanced. You should be balancing. We're just low on time, but that does it. You try a double replacement. Now I want to give you a little bit of mixed practice before we quit. Write this down. Predict those double replacement products. I know it's double replacement because it's two compounds reacting together. The aluminum is going to want to switch with the hydrogen because they're both positively charged. That means that nitrate is not going to move, and sulfur is not going to move. Hydrogen's going to come over here. Aluminum's going to go over here. Check what you wrote. +1, -1, we're good. +3, -2. This is a 2 to 3 to 6 to 1 mole ratio if you balance it. Now, nobody's asked me what about these reactions being a no reaction? Why don't we look at an activity series for double replacement? Double replacement does have the ability to be a no reaction, but we don't use the activity series. We use something called a solubility chart, which we're learning about on Tuesday, because we have one lecture left in this unit at a later time. If you're at home, pause the video, write these down, and solve them. I recognize the first reaction as being single replacement because there's a free element reacting with the compound. So looking at it, before I solve it, I want to make sure the reaction will happen, which means the element by itself needs to be higher on the list than the element that it's switching with. Platinum and hydrogen are both positive, so platinum would have to be above hydrogen. Is he? No. Number 1 is a no reaction. Looking at number 2, I identify him as double replacement because he is two compounds reacting together. If I start with the stuff that's going to stay, I know that sulfate's not going to go anywhere, and I know that hydroxide's not going to go anywhere. Calcium and aluminum are going to switch. So calcium's going to come over here. Aluminum's going to go here. Check what you wrote. We're +2, -2, so nothing will happen there. We're +3, -1. So cross. Looking at number 3, I recognize it as double replacement because it's two compounds reacting together. So I know that carbonate's not going to move. and the oxygen is not going to move. Magnesium and iron will swap. Iron will come here. Magnesium will go there. Check nomenclature. Now, some of y'all got confused on iron's charge, but if you look at the reactants, you can figure out iron's charge. It's ferric, because he had a charge of 3 on the other side. He must have a charge of 3 now. Carbonate is always 2, so we've got some stuff going on here. Magnesium's +2, oxygen's -2, so nothing will change on that compound. The final example is identified as being single replacement. We've got a compound and a free element. If you label the charges, iron and mercury are both positive, while the nitrate's negative. So iron and mercury want to switch, but make sure it'll happen. The free element needs to be higher than the bonded element. Is iron above mercury? It is. So this one will happen. So let the metals swap. That means that on the other side, nitrate's not moving. Just the metals are. Mercury is going to come over here. Now, this guy is mercurous. He keeps the 2 for a non-diatomic reason. If you studied your ion sheet, you know that mercurous exists and he's weird. But examine that. Don't let this confuse you. Examine it if you need to later. Iron is coming over here. It told us that iron's charge was 2.